Okay, we're gonna start our session for forecasting and near real-time monitoring of smoke and air quality impacts from wildland fires. My name is Jingqiu. I'm a HAQAST PI from University of Alaska Fairbanks. Today, our first speaker is Chen from University of Iowa.
Okay, thank you, everyone. This is Chen from University of Iowa. I'm glad to introduce our new HAQAST project about supporting air quality and public health management in wildfires, focusing on the satellite and machine learning-based PM2.5 forecast. Our science team member includes the Professor Jun Wang and research staff, as well as grad students in our Iowa group, as well as our co-investigator from UIBC and GMO. I would also thank the support from our stakeholders, Martha Webster, Dan Welsh, Bjorn Kim, and Leif Paulson to support this project. So we have already known that PM2.5 can cause significant health issue and mainly consists of fine particles. The wildfire smoke can significantly influence the PM2.5 pollution. And even through the analysis of only ground-based measurement, Burke et al. Have found that the wildfire smoke erodes 25% of previous progress in decreasing PM2.5 in most states in United States, even larger than 50% in Western states. As a result, the decreasing trend starts to reverse or stagnate in most states. A lot of efforts have been made to monitor and forecast PM2.5, such as we have ground network and also satellite to provide a near real-time measurement of the aerosol particles. We also use the chemical transport model to forecast the PM2.5 in large areas such as the continental US, CONUS. But there are still challenges to forecast PM2.5 under smoke condition. The smoke plume can rise to different altitudes, which always above boundary layer due to the fine particles of the smoke and the strong power from the fire. Then the smoke plume can transport to downwind region and causing the air pollution in large area. If most smoke particles located at higher altitude, there will be less particles at the surface. So not only total column aerosol optical depth, AOD, but also the smoke vertical distribution determine the surface PM2.5 concentration under smoke. However, until now, smoke plume rise is parameterized using diverse approaches in various CTMs and causing the discrepancies in PM2.5 forecast. The aerosol extinction profile observed by the LiDAR can help improve this PM2.5 forecast, but this improvement is limited due to the low spatial coverage of LiDAR. So it will be difficult for our stakeholders and air quality forecaster to apply those CTM forecasts for their specific area of interest. Fortunately, in recent decades, we have more and more passive satellite measurements that can provide the aerosol layer height information. Actually, our group has dedicated past few years to developing aerosol optical central height, AOCH, product from passive satellite measurements in oxygen A and B absorption band. This algorithm can be applied for both the hyperspectral measurement from tropomi, but also the image measured by like EPIC from the deep space. As the newest geostationary satellite, Tempo also covers the oxygen B band, making it possible to get the aerosol layer height distribution over CONUS hourly. Okay. Actually, I know that for most satellite data users and stakeholders, they are more familiar with LD data, and AOCH is a new parameter for them. So I would like to introduce the definition of AOCH first. Actually, this parameter is defined differently in different algorithms. In our algorithm, this LCH is defined as the altitude where the maximum aerosol extinction locate by assuming the aerosol vertical distribution follow a quasi-Gaussian distribution with a fixed halfway value. Even though it's single parameter to describe the whole profile, we have found that it's very useful to constrain the surface PM2.5 estimate. The left panels here shows a small case. We apply the troponin LCH retrieval as a simple scaling factor to scale the MER2 PM2.5, and we found that it can effectively correct the PM2.5 false alarm in the downwind region. With this success, we have developed a decision support system called FireAQ by combining the near real-time satellite measurement and CTM forecast with the support of last NASA HAQ program. The left panel here shows a snapshot of this FireAQ system. We visualize the daily average PM2.5 distribution in CONUS from 3 forecast systems, Giuseppe, Joseph, CAMS, as well as their ensemble result. We also visualize this air-null near real-time measurement here. And you can also see the forecast time series in the 72 hours by click any location on the map. We also visualize our near real-time satellite product related to wildfire smoke, including the modified combustion efficiency from our FieldDAT2 Weir's measurement to showing the burning phase of the smoke, such as the smoldering fire or flaming fire. And our troponin LD and LCH result here to show the smoke plume vertical and horizontal transport. So our new HAQAST project is trying to extend the capability of this FireAQ with 3 key objectives. First, to develop the hourly tempo UV aerosol index, LCH, and LD for wildfire smoke in CONUS and validate them. Then we try to combine the ground measurements, satellite observations, as well as the CTM forecast into the machine learning model to improve the forecast of this surface PM2.5 in CONUS. And also, we will evaluate the performance of this tempo LCH and machine learning forecast in decision-making activities through collaboration with our stakeholders. So here is the workflow of this project. At first, we will merge our troponin O2AB algorithm to the tempo data and do some small case study and validation. Then we will move this algorithm run operationally to provide near real-time product. And for the machine learning part, we will establish a baseline model to train the daily PM2.5 using the troponin LCH. And then we will move to forward mode to train the next day PM2.5. And finally, we will add the tempo hourly LCH and tune this model to forecast hourly PM2.5. So all of this new forecast and also new tempo LCH data will be implemented in our FireAQ system. Okay, here are some preliminary results. I can show a small case and the tempo retrievals we have done. You can clearly see the UV aerosol DAX, LD, and LCH all capture the smoke transport. And we evaluate our LCH using the new spaceborne LiDAR Earth here, and also ground-based AeroNet LD. We found our LCH and LD agrees well with those measurements. And you can also see some diurnal variation of LCH and PM2.5, as well as their correlations for this smoke plume case. Like for the fire source region, you can clearly see that the LCH value is really low, smaller than 4 kilometers, but the PM 2.5 is higher than 30 microgram per cubic meter. But for downwind region, this LCH is really high and can be higher than 8 kilometers, and the PM 2.5 is low. And for you can also see some descending of this smoke plume in the eastern side of the L1, and also the corresponding increase of the PM 2.5 value. Here are some preliminary results. We try to add this tropomi LCH products in our machine learning model, and we found that compared with those model without the LCH, we can get better results, like a little bit higher correlation and the lower root mean square error. And yeah, that's all I want to share, and I will look forward for more progress. Thank you.
All right, thanks, Xi. Our next speaker is Leif. Yeah,
You got it.
okay, all right, floor's yours.
Thank you, sir. If I advance here. So yeah, I'm Leif Paulson with Wyoming DEQ Air Quality Division. Also here with me at this meeting is Lauren DeVersi, our technical writer for exceptional events. And we just want to thank HAQAST for the opportunity to be here. And we look forward to having conversations with y'all throughout this meeting. Thank you. So what I'm going to be talking about quickly is looking at a couple of local wildfires near one of our ambient air monitoring stations in Wyoming. Just a little bit about us. I'll share about Wyoming DEQ, about our station, Pinedale Gaseous, the two fires, Dollar Lake and Willow Creek, and seeing the data from Pinedale influenced by wildfire smoke and our limited use of satellite data. I am certainly not a satellite data expert or guru. I appreciate many in this room are, though, which is good. And I'll try to share a few takeaways. So a little bit about us. As you can see on the map, we are here in St. Louis. Wyoming is further away. Our office for DEQ is in Cheyenne, Wyoming, in the southeast part of the state. There's Denver, to about 100 miles, hour-and-a-half drive south. And just in Wyoming, you can see Devil's Tower, Close Encounters of the Third Kind to the northeast. And our national parks of Grand Teton, Yellowstone in the northwest, Pinedale's in the western part of the state. About the Wyoming DEQ Air Quality Division, we're an air regulatory agency for ambient air monitoring, continuous emissions monitoring, permitting for new source review, Title V, stationary source compliance, and air quality resource management. In the state of Wyoming, we have around 25,000 permitted facilities, including over 100 Title V sources. Our air monitoring network, while we are 50th in population of 50 states, we have 26 active air monitoring stations that we own and operate and are available for you or anybody else to look at on YVisNet. Within that network of air monitoring stations, there are 7 monitoring objectives that the whole network covers, not just one individual station. And just want to say I've been here before. Check out in 2023, Lars Lone and I did a presentation on us, on our who we are, and then 2024 in Massachusetts about another little episode. So looking at Pinedale in the western part of Wyoming, it continuously monitors for ozone, PM 2.5, nitrogen dioxide, meteorology. And with our stations, we have cameras with them that get images every 15 minutes, which is a valuable resource when looking at wildfire smoke. Pinedale is the county seat of Sublette County, which is part of this purple outline on the map of our ozone non-attainment area for wintertime ozone. And also on the map, you can see the 2 fire perimeters, Dollar Lake north of the station and Willow Creek in the southwest of the station. The Dollar Lake fire started in the latter part of August. It was contained in mid-October, around 20,000 acres, unknown cause, and it's on the land ownership of the U.S. Forest Service, the Bridger Teton National Forest. You can see in the upper right, local photojournalist capturing the image. Then below in the time-stamped images are a clear day from Pinedale Gaseous and a smoky day from Pinedale Gaseous. Similarly, Willow Creek, around the same time, late August of 2025, containment mid-September, smaller fire, 4,000 acres, same land ownership, and again, just definitely images to convey smoke in the area. So looking at the station, Pinedale Gaseous, with our ambient air monitors there, what did we see? So for PM 2.5, we obviously noticed during the start of the fires in late August, uptick, including 3 exceedances of the 24-hour PM 2.5 NACs, and a few more elevated readings in early September. For gaseous, for NO2 and ozone, no exceedances. Maybe by our standards in Wyoming, we don't have the traffic problems of big cities, but maybe by our standards with the NO2, some slight uptick in August during the start of the fires. Ozone, we didn't really see anything. So how would we approach this from kind of an air regulatory perspective? We kind of start with AirNow Tech, looking at the continuous PM 2.5 data available from our stations and the others, and just seeing, I ran high split trajectories as an intro at different heights, 50, 1,000, 3,000 meters. And we can see in the red one, the 3,000 meter one, that it looks like there were some influences coming from Willow Creek, southwest of Pinedale. Not as much from Dollar Lake, given the other trajectories there. So not a whole lot to see with that per se, but we'll look at more evidence. We obviously see the fire detections from VEERS and just plain old worldview here, looking at the imagery from what we see and starting that. So most noticeably, stuff is happening. If I can click, right? So next, what I did, Aerosol Watch, looking at the Star-Nesdis Aerosol Watch website. Look at, on the left is one of the days from the event, August 23rd, technically not an exceedance day, but elevated PM 2.5 concentrations were observed at the station. And you can see just the meteorology in the left animation. Then on the right, I decided to play a little bit and adding goes west aerosol optical depth along with hourly PM 2.5 averages from Pinedale as well. And you can see, I think in the morning hours in this animation is when it was more pronounced at the monitoring station. Then, good, it's working. Then here, I decided to get a little creative and look at EPA's Remote Sensing Information Gateway product using Tempo NO2 vertical column troposphere level 3 data. Don't think there's any gaseous concerns as we kind of just looked, but I was curious to see if there was anything. And we can see Dollar Lake north of Pinedale just kind of transporting from west to east. And we can see as well a little bit of action from Willow Creek in the animation that as well there. There we are at the bottom in the southwest there. So kind of summarizing and thinking about things, some takeaways. There's some supporting evidence to suggest that smoke from Dollar Lake and Willow Creek influenced Pinedale's PM 2.5 data. Again, 3 exceedances of the 24-hour PM 2.5 NACs. And I mentioned, our main office is in Cheyenne. We also have field offices throughout the state for compliance reasons. One of them is in Pinedale. So I contacted the gentleman there who is in the field office because he is a local expert and knows the region well. And just from his 2 cents, yes, there was smoke from Dollar Lake that influenced Pinedale from his perspective. And I just want to maybe say here as a summary for other state and local agencies that are doing this and trying to try this, is that there are a lot of available tools to assist without needing to be an expert. Again, I am not an expert on satellite data or significantly committing time. Air Now Tech with the imagery from MODIS, seeing the PM2.5 concentrations, running those high split models. The NASA Worldview Imager point and click, seeing VIIRS and aerosol optical depth. The Aerosol Watch Star NESDIS product to see the meteorology and aerosol optical depth. I really like the remote sensing information gateway tool that EPA has for mapping purposes, getting some tempo data out of that as well. I cheated a bit and used our state of Wyoming uses Google for its suite, and I used Google Gemini just to say, hey, make me these graphs in R and RStudio that shine brightly and have the flashing neon light effects and everything we'd want to see. So there are a lot of good tools to assist. And I think I even looked at the HAQAST flowchart that was mentioned this morning as another resource. And not on here, I just want to commend the Western States Air Resources Council, WESTAR. They arranged some tempo training back in August in Fort Collins, Colorado for Western states, just to help novices like me and others just to learn and engage. So with that, again, I just thank you for your time today and just look forward to discussing further with you. Thank you.
Our next speaker is David Mendez-Jimenez and Glen Roussin from Missouri Department of Natural Resources. All right.
Hey, good afternoon, everyone. Thank you for having us. I'm David. I'm joined by Glen today. We're with the Environmental Services Program at Missouri DNR. He's with the Air Quality Assurance Unit, and I'm with the Air Monitoring section. We're here to talk about Missouri's efforts to monitor air quality data. So we'll start with the department's mission. Missouri DNR mission is to build a lasting legacy of stewardship for future generations. One of the resources that they want to particularly focus on is air quality, of course. In 1990, Missouri DNR had approximately 14 sites across the state, three staff operating each of these sites. Over the years, that grew to approximately 20 sites. You also had local agencies in Kansas City, St. Louis, and Springfield. And the same year, these sites were consolidated, and DNR took ownership of all the sites. Currently, we're based out of Jeff City, so now we have approximately 44 sites and have 9 staff members that do the field work to perform quality control site inspections at these sites. So this map is more representative of what our air monitoring network currently looks like. As you can see, there's a lot of air monitoring sites, specifically in the St. Louis area. The purpose of these air monitoring sites is to collect ambient air data, specifically of air pollutants. When we perform quality control checks, we're trying to validate the data coming out of these equipment and air monitoring sites. And we also make sure that the equipment is operating correctly. We perform approximately about 2,000 quality control checks throughout the year. The measurements are upwards of like 5 million data points each year. So in addition to that, Glen's unit here is responsible for ensuring our sites are sited correctly, and he performs performance evaluations.
Yeah, our goal is to do around 250 audits, performance evaluations. We're required to do 243, and this includes not just for PM 2.5, but PM 10, as well as the ozones, NOx, SO2s, as well as industrial sites like for Doe Run, because we deal with lead here in Missouri. So we have to audit those sites as well. And then we'll also with EPA, and we do national performance evaluation programs for PM 2.5 and lead as well. And those are comparison units for the regular PM 2.5 in the system, and they'll compare that nationally as well.
Yeah, so that was a great previous presentation where you guys talked about the end result, the data collection, and now you guys are going to see what we do on a day-to-day basis to validate that data coming from these air monitoring sites. So we'll start with the first one. A lot of our day-to-day work is basically encompassing, making sure equipment is working correctly. So we have a lot of equipment throughout these air monitoring sites. And one of the things that Missouri DNR does is we perform all of our work in-house to repair these machines and make sure they're working properly. Obviously, if they're not working properly, the data would be no good, right? So here's another example of some of the machines we work with. And like I said, we very rarely send any of this equipment back to the vendor just to save money and time. One example is a ozone pump analyzer repair costs $600, but we do it for $100. So a lot of work goes on a day-to-day basis. Sometimes we do have to repair entire sites. This is an image from the 1993 West Alton flood here close to St. Louis. A whole air monitoring site was demolished, and just a picture of some staff members cleaning up the debris. Two of these staff members are actually still there, so we got like 40 years of experience from these guys. So and then, as I mentioned before, the final product is quality control data. So all these measurements go through a quality control process each week to make sure that the data that we produce is accurate and representative of the ambient air in Missouri. Anything you want to add? So data is a big part of it, right? So I wanted to highlight two sites in Missouri that are, some of our bigger sites. Up top, we have the Kansas City air monitoring site in downtown Kansas City. It's a multi-pollutant site. It's of interest to local organizations there. We do have a history of working with local groups and organizations to install low-cost sensors, things of that nature, so that they can compare their products to our, regulatory grade data. And on the bottom is one here local to St. Louis at Blair Street, our biggest site in the network, multi-pollutant site as well. A lot of projects go on here. We have interest from vendors, local organizations, and a lot of research groups here at WashU that take interest in our data and use it for the research projects. So, yep, that's it. If you guys got any questions, feel free to reach out. Thank you for your time.
All right, so I'm not Aaron. Next speaker is Aaron Ager. And so because Aaron cannot make it, and I'm gonna fill in for his spot, so I'm gonna talk a little bit about what we're doing in Alaska for air quality monitoring for wildfires in Alaska. Just give you guys a little bit taste of what's happening in pretty far north. So I'm part of a HAQAST team. So for my HAQAST project, I'm gonna be working on two things: one is wildfire, one is dust. So I'm gonna talk about this wildfire in this session, and I will talk about dust in next session. Okay, so I'm sure you guys all heard a lot about wildfires, but wildfires is actually quite unique in Alaska in a sense that it's growing pretty rapidly, and there are a lot of studies showing that extreme wildfires are increasing most rapidly in Alaska. So that is quite extreme events. And also, Alaska is pretty large. Actually, this is something I have to really remind a lot of folks all the time, because this is almost twice as large as Texas. It's very large. And even when we do projections, it looks small on the map, but it's not really, and that's not really the case. So once things burn, we tend to have a lot of big burning area. If you look at burning area in Alaska, we have 4 million, 5 million acres of burning area. Sometimes can be almost accounting for 50% of the burning area in North America. So it's huge amount of burning. And also there are lots of unique features of Alaska fires. That is something also interesting and very much related to climate change. For example, border forest fires are mainly set by lightning, not by people. Not like in California, people actually fly to California to ignite fire, but that's not the case in Alaska, because you cannot fly into Alaska to ignite fire. There's nowhere you can land. So a lot of places they're just not accessible. So you cannot land your airplane and ignite fire. That's not doable. So it's ignited by lightning, and you can think about climate change, more convection, more warming climate in Arctic, more biomass. You may get more fire, more extreme fires. So it's something where we should not be surprised, and we would expect that to get a lot worse. And also another thing is that once things start burning, it's not really burning the trees. The trees are actually sparse. If you guys have a chance to go to Alaska for HAQAST maybe a couple of years from now, you will see that once things start burn, the trees are burning quickly and very quickly start burn the soil, the organic matter in the soil. That's often from litter and we call duff layer, and it can burn for long time, can burn for weeks, even months, because people actually consider fire is a natural process. They do not put out fires, they just let it burn. And so as a matter of fact, 60 to 90% of fuel combustion coming from the carbon in the boreal soil, not from the trees. So because it's coming from soil, it's a lot of moisture in the soil. It's actually the temperature is much lower compared to burning the crown, burning the trees. So because temperature lower, we have a lot more smoldering. So if you guys are doing all the fire experiments, you will know that the combustion efficiency modified MCE is lower. Therefore, you're emitting a lot more organic aerosols as a result of lower burning temperature, as a result of smoldering. So that's actually very unique emission. And here I'm just showing you a picture of this duff layer I'm talking about. You can see that this duff layer is very rich, actually spongy. If you guys get a chance to go to Alaska, I love to show you that. The soil, when you stand on soil, is very spongy because all the organic matters in there, you just keep burning for weeks, months. It's just amazing. And yet, it's because it's burning, as you can see from the left panel, lots of organic matter is being emitted for weeks, even months. That's just a natural process. Okay, so because of that, okay, so we have trying to understand the impact of wildfires in Alaska. So first study, I'm a geochem modeler, so we run geochem, we run landscape model. This is a work done by Mike Weston, Ziwei, and with in collaboration with Michael Han. We trying to run geochem model in Alaska to understand how wildfire impacting surface PM 2.5. What we found is that actually geochem, if you inject all the smoke in the surface layer, if you run a nasty model, the model gives you a high bias, unfortunately. We think there are allowed to do injection height. There's something can be improved in the geochem model. So instead of trying to play with injection height, we actually just use observation to calibrate model output. So we use all the prepare sensors to calibrate model output. Well, if you look at the right panel, it's a corrected PM 2.5. This has been reduced a lot by factor quite a bit. Therefore, we can get a more realistic model output of PM 2.5. From there, we can estimate the health impact of PM 2.5. So this is work done by Michael Han's group at UA and Ziwei in my group. So we're trying to come up with some metrics to understand the smoke exposure. So we look at the number of smoke waves and the length of longest smoke wave. And so we found that actually the place got the most hit by wildfire smoke is somewhere pretty far north. If you look at on the right panel, this is a dark blue area. That's called Yukon Flat. It's an area there's no surface monitoring at all. And it is a place we got the most wildfire smoke. It's kind of an interesting area. I think I'm trying to talk to local air quality agency to put more sensors there to understand this remote area, we get a lot of smoke, and yet there are no way for them to understand the impact. That's just something got to be improved. Okay, so after we run the global model, we started to use the regional model. So in 2020, NOAA decided to deploy this HERS smoke. I'm sure many of you have heard about this HERS smoke model in Alaska, and they have a domain in Alaska specifically to understand the smoke in Alaska. HERS smoke has some unique strengths because its resolution is 3 by 3 kilometer. It's much higher resolution than most global models. So we were pretty excited. So we started looking at HERS smoke right away. And turns out HERS smoke is not as, there's some bias. So if you look at the left panel is the HERS smoke compared to purple air. This purple air we calibrated with our research grade sensors. We can show that purple air, compare HERS smoke and purple air. HERS smoke is too low by factor of 5 to 10. HERS smoke, this is the state-of-art air quality forecasting model is too low by a factor of 5 to 10 in Alaska. This was kind of shocking. We showed this to the to NOAA folks. They were not surprised. So, but it really make us curious. What's wrong with the model? You know, we're a modeler. We really want to figure out, is that because we really wrong with emission by factor 5 or 10 or something else? Turns out we think it's something else. It's something. So Ziwei Dong, again, in my group, he start looking at this weather balloon from the all the balloons we launched in Alaska, compare this temperature vertical profile between model and the weather balloon. And we found that whenever there's smoke, heavy smoke in Fairbanks in this area, we always tend to see an inversion layer, temperature inversion layer from observations. So essentially you have this heavy smoke really heating up the air aloft. It causes this inversion, temperature inversion layer. You never see that in the model. Model cannot get that right because model does not have the inversion layer. Therefore, you have really strong ventilation. When you have smoke, smoke ventilated quickly, your model is too low. So that's actually make it really interesting. We think there's something beyond the emission strength in the model should be fixed. So here what we think, there's a positive feedback. When you have smoke, you have absorbing aerosols, brown carbon, black carbon, they can heat up the air above surface. Once you heat up the air above surface, surface is cooled down, you start developing this inversion layer, you're gonna trap more smoke, then smoke continue to keep going and amplify this effect. This effect got amplified, it got this positive feedback, you develop an inversion layer. Model cannot get that right, because it's CTM-ish, chemical transfer model, because you do not get feedback from smoke to meteorological field. Because of that, model is just wrong. We think this is part of the main reason for model bias, because we are not really that great in the model development, so decided using machine learning to fix that, because it's quick, easy, you know, you can get things right. You can bypass the complexity of physics. So we introduced this machine learning. We use the convolutional neural network. So we were able to fix this bias by say, tell machine learning model, here's model input, here's PM2.5 supposed to be. Machine learning can fix that right away. So it's pretty easy. And but that makes us think, how does machine learning fix this problem? So we start looking into a little bit details. What we found is that we give model two main parameters. One is vertical smoke, one is surface smoke. So model can redistribute the vertical smoke from aloft to the surface somewhat, then can fix this surface PM2.5 by redistributing smoke vertically. And also we compare this vertical smoke with purple air sensor. We found that vertical smoke has much better spatial temporal variability compared to purple air than the surface smoke. So indeed, the total column agree a lot better with the purple air, but the surface smoke in the original her smoke is not that great. So all in all, we were able to fix this. So right now we're trying to develop some system to really show improved air quality forecast. We've been working with local agency to put this model results in this ArcGIS system for wildfire management. This is a barcode on the left. This is a wildfire management for the local agency. And also on the right, we have a website to to put all the sensor data and all the model forecasts and there so we can further improve the model output. And so this is what we're doing with wildfire right now. Hopefully we can improve more in the next couple of years. With that, thank you for your attention.
We can invite all of the speakers to come back up and we'll have our Q&A.
Okay, maybe we can open for questions.
Hi, thank you. Adam Schlosser, MIT. So my question actually goes to you, Jingqiu, is ML AI methods are like very promising in terms of these types of forecasts. I guess my one thing that I would push back on is that just how you described it, I'm wondering if there's any concern that if you were to have a forecast, say, in a very unstable environment, so there's a lot of mixing going on, so you don't have that propensity of that inversion layer, or just in a very dynamically forced environment, does the ML algorithm pick up on that, or is there a concern about a false forecast in those situations? Or can you just sort of be proactive in that sense for these forecasts? So thank you.
That's a great question. So we've been looking at this ML correction, and turns out it does provide some positive bias, because when you distribute the smoke, sometimes there's not so much smoke distributing that. In the meantime, we also need to keep in mind that those appropriate sensors also have its own uncertainty. So together, right now, we do not see huge bias. In the meantime, we're also trying to use satellite AOD as a further constraint to make sure, even there are some extreme values, the satellite AOD could tell us what's wrong maybe there. So together, this is still in development, but hopefully with all the tools we have, fitting more to the machine learning model, we can do a more stable version of the correction.
Hello, I have a question for Jingqiu for the wildfire in Alaska. Thank you for your presentation. I have a question regarding the terminology used. So you are comparing the HER smoke with the purple air. HER smoke doesn't give any PM 2.5 concentration. You only have the smoke. So what you are actually doing is that you have the HER smoke, and then you use the purple air for the bias correction part. But what is the bias here? HER smoke doesn't give any PM 2.5. This is more like estimation, not bias correction.
That's a great question. Okay, let me back up here a little bit. First of all, her smoke does not have PM 2.5. It does have smoke PM 2.5. So it's the PM 2.5 only due to smoke. That's the beauty of Alaska. We do not have much anthropogenic emission in summer. Not at all. I can tell you it's about 1 microgram per cubic meter. So we've been looking at this for a long time. The main source for organic matter or PM 2.5 in summer is from wildfire. So we assume the PM 2.5 we're seeing from purple air is purely coming from smoke. I think that's give you maybe at the most 10% bias. So that's not a big deal. And we also calibrate purple air with research grade sensor from local air sites, like Department of Environmental Conservation. They have this BAM, and they also have, I forgot, the measurement, the mass gravimetric measurement of PM 2.5 mass. We use those things to calibrate our purple air. We found that when we also apply EPA recommended method, we can see if we reduce purple air by factor 2-ish, they agree really well with EP air now sites research grade sensors. So we use that corrected data as true purple air data to compare with her smoke. I don't know if that answered your question.
Yeah, that answered my question. Thank you.
Okay, I have a question real quick. I'm always interested in the states because I feel like every state has a different way of setting up how they reach out to communities and how they divide themselves in different divisions. And so I'm just curious, like, for your, what you would most like to have, like what data sets or what tool at like what end of when, especially when there's smoke in the air, like for you, is it like the forecasting is critical, or you would like more on that? Or is it like what's happening right now to communicate to people? Or is it more like after the fact and like trying to figure out the impact? And I'm just curious sort of how, from your perspective, and like how you interface maybe with other entities, whether that's like the health side of things or, planning for prescribed burns, if that impacts you.
So great question. Well, with us in Wyoming DEQ, we're strictly an air regulatory agency. There are boundaries with us and the Department of Health in Wyoming. We do try to collaborate and release and collaborate with the National Weather Service field offices in the event that smoke is forecasted. To alert the various NWS field offices. So for Pinedale, if I remember my NWS maps, that would be the Riverton, Wyoming field office and they would then get local local alerts on smoke and providing just some basic information and links to, I mentioned the YVisNet website where the Pinedale data is at to see that. So I think probably forecasting as it happens, because just, just even offline, off duty, you just see people on social media. Where's the smoke coming from? And that is kind of to just seeing that a pressing concern when it happens, but that's at least our perspective.
Missouri is about the same for regulatory as well. But to get information as it's happening is also beneficial to get reporting into St. Louis and Kansas City areas, because a lot of our smoke, I mean, we'll get other areas too, but most of ours comes from Flint Hills in Kansas. So that's where a lot of our big problems come from, and that's smoking from that area.
We'll add that for our program specifically, we're the environmental services program. So we do a lot of the field work and data validation, as I mentioned. But our air pollution control program would definitely be more interested in, real-time, alerts. Whenever there's a wildfire event, our air monitoring sites definitely get a hit. And the air pollution control program would be the one who is, more interested in the regulatory side of things, where in terms of, exceptional events, Missouri just recently submitted their first exceptional events for the 2023 Canadian wildfire smoke. So yeah, that's definitely one of those things where not only is it important for real-time measurement to alert the public, but also for that regulatory grade and attainment designation.
Okay, thank you for that. And also for the Flint Hills, I know we have, I'll shout out Emily and Amber's work in the last HAQAST, really did a close look on that. And I know Emily and Amber, and as well as Aaron, who can't be here today, have projects doing a lot more with prescribed burns and quantifying that. So we have a question from online. How are you processing, I guess this is for you, how are you processing purple air before comparing it to the model? Are you applying the EPA correction, or have you developed your own adjustment based on local co-location studies with FEM monitors?
Actually, I did not do work, and my student did the work. So my understanding is that we do both. We compare, we do the EPA recommended correction and compare with the local monitor, and they agree pretty well. So that was our final decision, is we take both into account, and turns out EPA recommended correction that from the paper in 2020 works pretty well for us in summer. Of course, that correction can be temperature dependent, so we only focus on summer to use that correction. Because when it's winter, you have relative humidity, all kinds of other things that, or the ice crystal can mess things up pretty easily. So we focus on summer, and that correction turns out working fine.
Oh, okay.
You go first. Okay, thank you. I'm curious about how state government decide where and what pollutant to measure. Like, what factors are you considering, and do you have any guideline to follow? And have you ever collaborate with a research group to decide how to deploy it?
Yeah, definitely. I think a better question, or a question that could be better answered by the air pollution control program. If you have any questions with who to contact there, we can give that information out. But I will say, we do work closely with the air quality analysis section, and they're the ones who, determine what areas need air monitoring. And I know they definitely work with the local universities to determine, what's an appropriate location for monitoring a new pollutant. They definitely take that into account. I don't remember one off the top of my head, but I know we have had discussions before with the professors from SLU, St. Louis University, with regards to implementing new NO2 monitoring in the St. Louis area. So things of that nature, we're always open to collaboration. So if you have any more specific questions, we can definitely relay that to them.
And if I may chime in just for another perspective too, we We just look at every 5 years, the EPA requires a deep dive of a state or local air regulatory agencies monitoring data. Network assessment is what it's called in the CFR. And that kind of provides an opportunity for area served analyses, lots of population polygon maps, looking at where have we not been to, are we missing an area, are we, you know, and such. So that kind of guides us in Wyoming a little for ideally where to go. So just in Wyoming, we are privileged to have mobile trailer monitoring stations that can be parked with power, with land use, siting criteria, et cetera, parked and we can park it there for a year or more, and it has a complete suite of all the criteria, pollutants, and meteorology as well to just conduct introductory monitoring to at least to see, okay, did we notice anything here, or is there further reasons to continue on here? Do we move to our next location based on this assessment document?
I have a question about the Tempo aerosol height product for Chen. I was wondering, so it makes sense, lower aerosol layer height tends to correlate with higher PM concentrations versus like a higher aerosol height tends to correlate with lower PM concentrations. But I was wondering if you noticed cases where it was a high aerosol height, but it was like a thick, dense plume. So then there were still surface concentrations that were quite elevated, and how you handled those types of cases.
Okay, that's a good question. Actually, we haven't found so many cases as what you described, and I think this, since small particles always fun, so they are easily to be lifted to high altitude, especially in the downwind region. Maybe in the fire source region, you can find really thick, smoke clear, and the high PM 2.5. But our aerosol layer height, that's some kind of describing the aerosol extinction. Actually, that's some kind of that's not a direct describe the particulate matters or aerosol matter the matters mass, but that's we have to assume that like the small particles within this plume like have similar particle size and similar composition. So that's so near the fire source, our product will be, it will be hard for our product to show the smoke distribution there, and our product have better performance in the downwind regions.
Thank you.
I have a question for Dr. Chen as well. So we found 3 types of injection height products. One using UV vis or oxygen, and one like MISA kind of retrieval, and the other is the thermal infrared. I'd like to hear about your comments about how they perform in different environments and what's best to use in different conditions. Thank you.
Yeah, thank you. That's a good question. Actually, I think they use different techniques to detect these fine particulate matters. And actually, for the the oxygen absorption band that's in the UV channels, and it is sensitive to like both fine particulate and coarse particles. But for the thermal infrared, they will more sensitive to the coarse particles. That's more you'll find more in near the fire source region. And also, if you use some like geometric method like the MISA, they will use some technique like the image recognition to determine this injection height, and those methods are more effective in the near fire source region. And if the smoke plumes start to diffuse, their technique it does not work well. But our technique work better in the downwind region. So yeah, I think combine different techniques, you will get a whole picture of how wildfire start and transport.
Hello again. I have a question for David and Glenn. You mentioned that you had an issue with lead, and I was curious what the sources of lead would be there. Are there a lot of, personal planes that still use leaded gasoline, or yeah, just what the sources there are?
Doe Run is a mining area that they mined for lead many years ago. And so they're in a massive cleanup basically for years now. And so we're still, they are, and we are still monitoring the lead levels in those areas.
So the lead are blown up by wind, so they are basically dust.
Dust in the ground as well, too. We have Herculaneum City where was the big manufacturing plant that had the lead facility there, and they tore that down. So, but they're still monitoring the lead in that vicinity, in that area as well.
Another thing I want to mention about lead is that for recent LA fires, that they found there are lots of lead, and because all the buildings have all the paint, they kind of being covered. But once you burn the buildings, that all the old paint can evaporate, make the lead. So it turns out there are lots of lead from LA fires. This is from network I'm part of. It's called a SAN network. So we're monitoring metals aerosol composition in real time, so we can see there are lots of lead coming out of and chlorine as well, because the plastic, when you burn the urban fires, you actually have a lot of nasty things coming out of. And the lead is very common for urban fires, not necessarily for the forest fires. So this is a different ways. We got different things like Boulder or Colorado, when they burn things there, you would expect some lead. That's something I think.
Well, that if you have any questions or where you want to, if you like to see a map where we have the lead samplers where we monitor for lead, you can always reach out and be happy to provide that for everyone.
I have a question to follow up on that. I'm just curious. I guess I think the state agencies, you have a lot of issues to handle all at once, and I'm sort of wondering how you kind of prioritize these different pollution sources or focus. Like, is it just driven from federal regulation, or do you have some leeway on the state level, or just different demands come up that you can switch, or how does that work?
Well, as mentioned there, Wyoming, we also deal with the network plan as well, but we have state implementation plan that we help monitor all what needs to be monitored as well.
Right, we just follow CFR. I mentioned at the start of my talk that some of the facilities, all those facilities have, not all of them, but in their permits, they may have, PM10 monitoring for the coal mines or Trona facilities in Wyoming, that we have to, kind of review their data and reports as well. So it does kind of stem from regulations and permits and that.
I also want to highlight our environmental services program does have an environmental emergency response team. And, for example, this year they had the St. Louis tornadoes come by, and they were the ones who were responsible for the deployment of on-site monitoring. So we work with them to provide suggestions, but, things of that nature that falls under, their jurisdiction, so to speak. So but that's another additional air monitoring that we do for the environmental services program.
Thank you. Are we in a, okay. Oh, no.
Yeah. So this is maybe going a little bit outside the scope, but another source of uncertainty in forecasting wildfires and the smoke impacts is forecasting the behavior of the fire itself. Is where is it initiating? Where is it spreading? How fast is it spreading? What's it? What fuel is being burned, and so forth. So it's a general question to the panel to talk a little bit about efforts at constraining those forecasts, not necessarily the smoke forecast. If you have any general comments on that.
Okay, yeah, that's an interesting topic. Yeah, I think we will need more measurements and more data related to the wildfires. Actually, not only related to smoke, but also fire itself. And we also need to know the meteorological conditions when the fire happen and how the convection happen. And so I think a lot of parameters and conditions we have to know or to involve in the forecast model. And I think that's still, a big development and research. Yeah.
One question that I feel like I hear a lot from people, especially, well, with satellite data, when you're looking at smoke plumes and you're trying to figure out how that's affecting the air pollution, but then you have these big clouds and thinking about how do I filter out, clouds, but also when these plumes are big enough, they're going to look like clouds. And I'm just wondering if you have sort of general advice to new users of the best ways to do that.
Okay, yeah. The cloud is always the issue for our aerosol remote sensing from satellite. Yeah, so that's why yeah, a lot of research start to use the machine learning technique to try to fill the gaps of satellite measurement by combining some ground-based measurements together. And I think it will be a useful tool to provide the gapless distribution of the satellite observations. Yeah.
Okay, so someone had asked with our lead conversation, are any of the fires burning, are there any fires burning in regions with lead or worse? So like I said, I hope the answer is no. Okay. Yeah, that's an interesting thing to think about though, if that happened. And it would be great to begin to get lead and other constituent deposition into a database to warn the public downwind during and post fires. Do we know anyone who is working on this? It would be great to get that. And the answer, I guess, is we don't know who's working on this deposition. Yeah.
I don't know anyone, but we do the composition measurements, but right now, not much. I would think that you would need to quantify that first. And for different field type, different fires, you may have different amount of lead and metals in the fire. So maybe urban fire tend to have more metals, heavy metals in there. Maybe there should be more strategic thinking first and the quantification before we really dive into that, I guess. Because we need infrastructure to measure those things first. Right now, if you look at improve or filter-based network that's often only get 1 point per day, then it's not necessarily can address this high resolution plume. You need a high resolution to really tell you how much, because if you average over 24 hours, not necessarily give you enough spike. But this is going to be a new challenge. I think we're moving towards a new era with all the high resolution data, everything. We need to think outside the box right now.
Hey, this is for Jingqiu. Earlier in the previous session, we heard from Randall about the sort of success in the eastern coast of the U.S. with mitigating a lot of wildfire pollution. And I think a lot of that is particularly attributed to the fact that we have a lot of prescribed burning over the southeast especially. But you mentioned that Alaska is vast and doesn't necessarily have a high population density across the whole state. And so I'm curious if you're aware of what pollution mitigation strategies exist now to deal with this increasing wildfire issue that you described earlier.
That's a multi-billion-dollar question. I think we're just discussing what type of forest management, fire suppression we should think about for different scenarios. And again, it's vast. Sometimes if you want to contain fire in a remote region, maybe different from California. So how do you, we trying to introduce a little bit of prescribed burning, but people are still very reluctant to do that at this point to mitigate the risk. It's been discussed right now. I don't think we have a good solution yet.
Yeah, and I guess the follow-up to that would be is that how much exposure is there going on in Alaska? Or is this more so for perhaps the issue is more so for people downwind of Alaskan wildfires?
And right now, Alaska has 700,000 people, so that's
not a lot.
Not a lot of population-wise is not a lot. But if you think about in the future, maybe 10, 20 years from now, I think people are going to move north because it's getting hotter and hotter. And so maybe it's a different game in 10, 20 years. In the meantime, global warming, Arctic warming is much faster than the rest of the world. So we need to have a long-term plan. When I was in Europe for a year, like 2 years ago, I spent a year in Europe. They have this really nice managed forest. They do not have wildfire in Europe, not much so, unless in Russia. So but they had spent a lot of money and effort to do that. So is that really worth to do that in Alaska or Canada? Because right now we cannot control Canada. A lot of Eastern folks are actually opposed to the Canadian smoke. Not much you can do, yeah. Right? So it's a whole Arctic question. That's something we were discussing that, there will be an international polar year in 2032. What we should think about, what question we should address. Maybe this is a good question to address.
Thank you.
Well, do we have any other questions? I have one more question. So we had mentioned a lot of different tools that you use to monitor things, and I'm just sort of curious, across the spectrum from your low-cost sensor to, calling your friend up in the city to tell them these are, what's the best way, that you find to sort of overlay satellite data or make the most use of like plugging in these different resources to get the most information? Because I know for a lot of these tools, like, we're not going to necessarily get the lead information from satellite, for instance. So I'm just kind of curious of like, what are better ways to sort of integrate with existing systems?
Oh boy. Yeah, well, I do like those local resources of calling up a field office employee that knows, oh yeah, that was that 2 weeks ago, Leif, the best to me is, bias here showing federal reference method, federal equivalent method monitors, but those are just expensive and requires, as Missouri presented, employees to do monthly maintenance, semi-annual or annual audits, requiring a lot of time and resources for the best, which is the challenge. And there's only so many community, so many dollars available, so many community and probably more communities than dollars available to put all of these top shelf monitors at. But just from that perspective.
Yeah, I'll add to that. I actually really enjoyed your presentation because I was unaware of like some of the tools that that are available to our agencies or even the public. So just being aware of what tools are out there. I think that's pretty important at a minimum.
Yeah, with us, we have like near road sites, like in St. Louis, near Ryder Trail and Forest Park. We have a near road there as well. In Kansas City, we just replaced our other one with a newer one. So that helps, with the impact of pollutants, around the interstate. But then we also have, we showed the main site for Blair that we have every pollutant and then some more that we're monitoring there for metals and stuff like that as well. And then we just have, regular background sites like Mark Twain State Park, where we monitor ozone, NOx, SO2, PM10. But yeah, we just, throughout the state, we have different areas and we try to cover for pretty much everything in those areas. Yeah.
Just going back to Tracy's sort of opening remarks on how she wants to focus HAQAST more on the private sector. I'm wondering, as state agencies, you seem to do a lot of stuff in-house in terms of measurement, but of course, I'm coming from more like the greenhouse gas side of things, which is what I've been working on for a long time. But in that space, there's a lot of climate tech groups coming up doing measurements for states, for companies. And I'm wondering how you interface with sort of the up and coming private sector for air quality monitoring. Because I wonder if there are sort of cost savings you can do as well as improvements in innovation by working with some of these groups that are trying to put in sort of private monitoring stations.
Yeah, I guess, not a lot of work that I know of other than, some vendors definitely reach out and, I like to, say I have an open door policy, I mentioned that Blair site, a lot of testing goes on there where vendors will reach out and they'll provide new equipment that they're testing. And obviously they want the data that we collect, to compare, to FEM or FRM data. So that's like been pretty good for us, just to learn new equipment and, for the vendor to, have that open door policy, if you will, with us, and then, more projects come out of that. So definitely, being able to, network that way is pretty helpful for Missouri DNR, I think.
And, we're a little different in Wyoming. We do rely on contractor support for the gaseous and meteorological monitoring of these stations. Pinedale is, the station I mentioned is kind of the day-to-day data validation, and some of the maintenance for quarterly visits are handled by a third-party contractor just for the sake of time and resources. So there is a good relationship with third-party vendors and small companies if we wish to consider purchasing a low-cost sensor or something. So.
Okay, well, with that, I think we're at time. So I'd like to thank all of our speakers for their excellent presentation.